welcome to my new lecture. In this video lecture I am going to talk about second law of thermodynamics and entropy in real world engines like Carnot engine and Stirling engine. These are topics 20.4 and 20.5 of the Halliday, Resnick and Walker book Fundamentals of Physics. First of all, we would look at second law of thermodynamics. Before going into the discussion of second law of thermodynamics in a formal way, in terms of defining it and its expression, etc., I would first like to elaborate a few conceptions related with the previous lecture. In previous lecture, I told that entropy of a reversible process or change in entropy of a reversible process is always greater than zero for the case of a irreversible process. Then I modeled this irreversible process with a reversible process in which there was a gas molecule confined in a container like this, and it was connected with a piston. Piston could be moved up and down, and there was a thermal reservoir which is used to provide heat. It may add heat to this container, or it may remove this heat from the container. Now, as I gave the expression delta S is equals to Q by T, and the question comes in mind that when the heat is added to the system, entropy should increase, or change in entropy should increase. What happens when this heat is extracted from this reservoir? Then the Q should be negative. It means that the change in entropy or entropy of the system should decrease. Is it reasonable or not? We would first look into it, then we would define second law of thermodynamics. Another thing that we need to look at is that I gave this definition of delta S greater than zero for an irreversible process. It was a closed system. Does this whole system, reversible system, represents a closed system? No, it is not, as the container is a different and thermal reservoir is something different. So it is not entirely a closed system. Now, to clarify all these points, I am making this whole as a closed system. Now, thermal reservoir has become a part of this closed system. Previously, thermal reservoir was not part of that closed system. Now, let's see what happens when heat is added or extracted from this system. We can also discuss these points in terms of a PV diagram. For an irreversible process, we took that the system undergoes a thermodynamic change from point A to B in a irreversible manner, raising its volume between these 2 points while keeping the temperature constant. This was our assumption in our previous discussion. This is for the case of irreversible. And if we have to make it reversible, then we have to basically reverse it from B to point A. Then it would represent a reversible process. First, it is from A to B, it is reversible, and if we make this system to to go from B to A, then it would become reversible. Now, in first case, heat was added to the system and piston moved upward. And we have made this a closed system and included thermal reservoir in it. When we have to basically make it to go from B to A, we have to extract the heat from this container to this thermal reservoir. It means heat is extracted from this container to this thermal reservoir. Now, if I write down the amount of heat, its magnitude to be absolute as Q, then the amount of heat extracted from gas or container should be minus Q, as it is extracted from this reservoir, and amount of heat added to thermal reservoir would be plus Q, as the heat extracted from this gas container is added to this thermal reservoir. So I have taken this to be positive, and since extraction of heat from this reservoir would be represented at minus Q. Now, if I write down delta S for this case, it should be minus Q by, let's say it's a isothermal process, it is T, and for this the entropy change should be plus Q by T. Now, if we see, we want to calculate overall change in entropy, that should be plus Q by T minus Q by T. This is net change in entropy. So these two will get cancelled out and we get a very useful result as 0. So one can see that if I make this process reversible, the change in entropy would be 0. This means that change in entropy is either greater than 0 or equal to 0, but it never decreases. This basically will lead us toward second law of thermodynamics, and this greater than sign is for a irreversible process and equal to sign is for a reversible process. And there is another assumption that we are dealing with a closed system. So second law of thermodynamics states that in a closed system, entropy increases for an irreversible process and 0 for reversible process. It never decreases. This is our second law of thermodynamics. This is our second law of thermodynamics, that in a closed system, entropy or change in entropy increases for an irreversible process. It increases for an irreversible, and zero for a reversible process. It never decreases. However, in the real world, almost all processes are irreversible to some extent because of friction, turbulence and other factors. So the entropy of real closed system undergoing real process always increases. Processes in which the system entropy remain constants are always idealization. So the concept of this change in entropy equal to zero is an ideal case. In all real world processes, the entropy of the system always increases. In the next step, we want to calculate force due to entropy. As an example, consider a piece of rubber on which we are applying a force F to stretch it. The rubber always resists this force of stretching. And by first law of thermodynamics, we know that change in internal energy is change in amount of heat minus work done. Now, when we are applying force to move it over here, the force by the rubber would be in opposite direction. Because it resists, this F should be in opposite direction as the rubber resist this stretching. So dW should be minus F, and let's say by applying force we are able to stretch this rubber by a distance dx, right? Then this would be dW is F dot d, or we can write it here as F dx. This negative sign is because we are calculating the work done on the rubber, and the rubber resists this force of stretching. And we can also calculate change in entropy, differential change in entropy, to be ds to be equals to dq, and if the temperature remains constant, it should be T, and dq would be equals to T ds. Putting both the results into equation A, I would get dE, change in internal energy, to be equals to T ds minus minus would be plus F dx. If the stretch in the rubber is not very much, there is a very small stretch in this rubber, the change in internal energy would be zero. This shows us that force in this case would be equals to minus T ds by dx. The temperature is constant, so the force depends upon the change in entropy, and this force is against this change in entropy because it is negative of it. You might have seen this in your life. Whenever you stretch a rubber, there is a force in your hand, and this force is due to change in entropy of that rubber. Rubber consists of cross-linked polymer chains, and when we stretch the rubber, the disorder of the molecules decreases as they begin to align themselves. So as they align themselves, their disorder decreases, so it means that the entropy of these chain molecules decreases, and we feel this change on entropy in our hand. After calculating the force due to entropy, I would move the focus towards entropy in real world, that means in case of engines, and this is topic 20.5. The engines take heat energy from a high temperature reservoirs and they make use of this energy with the help of working substance, and some of the energy is released to the low temperature reservoir. Working substance is different in case of different engines. In case of a steam power engine, water is used as a working substance, and in case of automobiles and other such petrochemicals such as gasoline, diesel oil, petrol are used as working substance, and some of the heat energy is released to the low temperature reservoir. And for the efficient working of the working substance must operate in a cycle. So all the working substances pass through a closed series of thermodynamic process. These are called strokes. You might have heard in case of motorbikes, 4-stroke engine or 2-stroke engine. So they work in working substance in closed cycle. Before going into the discussion of real world engine, let us first discuss what is an ideal engine. In an ideal engine, all processes are reversible. All processes are reversible and no wasteful energy transfers occur due to turbulence, friction, etc. So in case of an ideal engine, there is no wastage of energy due to turbulence, friction or any loss like that. We would look into the engine proposed by a famous French scientist in 1824, and this was supposedly an ideal engine, and he named it as Carnot engine. The basic process in all the working engines is like this, that there is a high temperature reservoir, and this engine takes amount of heat energy QH from this high temperature reservoir, and there is a working substance in it which basically works on this heat and produces work W, and some amount of heat energy QL is released to a low temperature reservoir. This is the basic working of all the heat engines, that they take heat energy QH from constant high temperature reservoir TH and convert this heat energy into work with the help of a working substance, and amount of heat QL is released to fixed low temperature reservoir, which is kept at TL. This can be represented by a series of thermodynamic processes which I am going to discuss right now. Let's look at in a PV diagram. Along this axis I have volume, and along this axis I have pressure, and first this is my initial point A, and as this heat engine takes amount of energy QH from this high temperature reservoir, this represents the case of an isothermal expansion from point A to B, and this is at temperature TH. Now this, at the same time, some of the heat energy is released to the low temperature reservoir as QL heat to this low temperature reservoir. This is an example of isothermal compression, because when heat was extracted and added to the working substance, it was positive from A to B, and when heat is extracted from this working substance to the low temperature reservoir, this represents as heat is removed from it and given to low temperature reservoir, this represents an isothermal compression. So I represent the isothermal compression to be like this. Let me call this as point C and this point as D. This is isothermal compression in this case. To make this process reversible, since we have taken isothermal expansion and compression, we have to make adiabatic expansion and compression in series with this expansion. So after this isothermal expansion, when the volume it was increasing, I would be making it an adiabatic process from B to C. This BC would be an adiabatic process, and this would be an adiabatic expansion, and the same should be done for this is if BC is adiabatic expansion, then I have to make an adiabatic compression from D to A. So one can see that from A to B, first isothermal expansion and then adiabatic expansion is, or adiabatic process is added in series with this expansion. And similarly, in case of compression, of isothermal compression, this dA is added as a adiabatic process to make it a reversible. Now I would say that AB is isothermal expansion and BC is adiabatic, CD is adiabatic process, you can write it. CD is isothermal expansion, and dA is once again adiabatic process. AB and CD occur at the same time, and BC and DA occur at the same time, and both of them occur in series to make it a reversible process. Now, if we want to look at the work done by this Carnot cycle, first is when there is isothermal expansion and adiabatic process A, B, C, you can find the area under the curve would be like this one, right? And when you have this CDA, the area under the curve would be this one. And when you calculate the net work done, this odd would be cancelled, and you have net work done, which is basically by this path. W would be A, B, C, D, A. This whole is basically the work done, as I am representing it like this. This filled part is net work done, right? This would represent my net work done by this heat engine, as this all would be cancelled out, and one can see that the net work done would be positive in this case. Moving forward, I am actually interested in calculating the entropy of this whole Carnot engine or Carnot cycle, and we know that the entropy is related with Q over T. This is general expression for it, and I have to represent my PV diagram, or basically model that PV diagram onto a temperature and entropy curve, because the entropy is related with temperature and amount of heat. As the case AB was of isothermal expansion, it means that between A and B, when amount of heat QH is added to the working substance, the temperature remains constant. On a TS curve, I would represent this AB like this, because it represents this AB represents a constant temperature process or an isothermal process. And since BC was an adiabatic process, in an adiabatic process, since no heat is added or removed from the system, it means Q is equal to 0. When this Q is 0, it means change in entropy is 0. So between B to C, I can say that the entropy is, change in entropy is 0. Since BC, and then for CD, it was an isothermal compression. It means that in an isothermal compression, as the temperature remains constant and entropy should decrease, because heat is removed from the system in case of CD. And last case, DA was of an adiabatic compression. In this case, once again, the change in entropy should be 0, as it represents an adiabatic process. So I would go like this. This is my whole Carnot cycle in terms of temperature entropy curve. So after this, I would look into calculating the work done during this Carnot cycle. Once again, I would consider the first law of thermodynamics, as I know that according to first law of thermodynamics, change in internal energy should be equals to Q minus W. Since it's a cyclic process and a reversible process, therefore for a reversible process or a cyclic process, change in internal energy is 0. This delta E internal should be 0 and Q would be equals to W. Now one can see from this expression that work done is equals to the net amount of heat energy that is transferred to the working substance. And this net amount of heat energy, as it has taken the amount of heat energy QH from the high temperature reservoir and released QL to the low temperature reservoir, so its difference has been converted into work. So the work done in a Carnot cycle is or in a Carnot engine is equals to QH minus QL. I may call it as equation B. Next comes the entropy in case of a Carnot engine, and there are two types of heat energy transfer in a Carnot cycle. One is when amount of heat QH which is extracted from high temperature reservoir to the working substance, and the other one is amount heat QL which is released by this working substance to the low temperature reservoir. So the overall change in entropy should be equals to change in entropy of the high temperature reservoir plus change in entropy of the low temperature reservoir, and change in entropy of the high temperature reservoir is plus QH by T, and since heat is released by working substance, so it should be minus QL by T. This gives me change in entropy. And if I consider the case that that for a reversible process the change in entropy is 0 as given by second law of thermodynamics, then I would take this delta S to be 0 and QH over T would become equals to QL over T if I use the statement of second law of thermodynamics. I would like to write this as equation C and this as equation D. From equation D we know that it should be TH over here and TL over here, TH over here and TL over, since they are different. Now for the case of this whole Carnot cycle, we know that this TH should be greater than TL because it's a high temperature reservoir and this is a low temperature reservoir. This leads us to the conclusion that heat energy of high temperature reservoir should be greater than the amount of heat energy which is given to low temperature reservoir, and this is another important conclusion from our discussion. In the next step, I want to calculate the efficiency of Carnot engine, and since this efficiency is in terms of heat, so it should be termed as thermal efficiency, and it is represented by this sign, and it should be equals to energy that we get from a heat engine and energy we pay for. The energy we get from this heat engine is W, and energy that we pay for is QH. That is the amount of heat that is transferred from a high temperature reservoir to the working substance. And if I substitute this value of W from equation B, I would get QH minus QL over QH, and this efficiency comes out to be 1 minus QL over QH, right? Now this efficiency, looking at it, efficiency becomes, if we calculate it in percentage, then we have to multiply it with 100. And if this QL is 0, it means the engine is 100% efficient. And what is meaning by this QL equal to 0? This means that no amount of heat energy is transferred from working substance to the low temperature reservoir. And this efficiency would be 0 if QL is equals to QH. This is not possible because we have already discussed that QH is always greater than QL. So practically this factor should be less than 1, and efficiency of a Carnot engine, of a real Carnot engine would be less than 100%. I can write down this efficiency to be 1 minus QL over QH, and since this is analogous to temperature, it should be 1 minus TL over TH. And if you want to calculate its percentage, you can multiply it with 100. Now looking into our discussions that TH is always greater than TL in case of an engine, one can say that efficiency should be less than 100%. And we come to the conclusion that there is no heat engine that takes heat QH from a HTR. HTR means high temperature reservoir, and converts it completely into work. There is always some value of QL, that is heat transferred between low temperature reservoir and working substance. Without sending any heat QL to low temperature reservoir LTR. To summarize this Carnot engine, we say that Carnot cycle is mere an assumption, and 100% efficiency is an ideal case, and in all the practical cases the efficiency is less than 100%. Take the example of a car. According to Carnot cycle, its efficiency should be 55%, but practically the efficiency of a car is 25%. Similarly, a power plant is considered according to Carnot cycle to be 40% efficient, but practically it has an efficiency of 30%. So practically Carnot engines efficiency is not achievable by real world engines. I haven't given this a name, let me call this as equation E. And one thing I want to clarify here is that all these results are for the case of a Carnot engine or a Carnot cycle. These since not all the engines are according to Carnot engine, so these results are only applicable to those engines which obey Carnot cycle. Other engines like Stirling engine or other different forms of engine, since they do not have Carnot cycle, so these results cannot be applied directly there. Now I would look into another famous engine, and that is known as Stirling engine. Stirling proposed his work I would like to represent this Stirling engine in comparison to Carnot engine. Let's see it with the help of a PV diagram. This is volume axis, this is pressure, and let's say that from A to B it is same like as that of a Carnot cycle, as it represents an isothermal expansion. But and reverse of it is from when we say TL, it acts in reverse order like this. I should be rather making it more, this would be more appropriate. Okay, you can manage it. This represents C to D and an isothermal compression, and both of these occur at the same time, as QH and QL are the amount of heat energy taken from higher temperature reservoir to working substance, and QL from working substance to the low temperature reservoir. The difference between the Carnot engine and Stirling engine is that in case of an isothermal expansion was followed by adiabatic expansion in case of Carnot engine. However, in case of Stirling engine, this is followed by isothermal expansion is followed by a constant volume process. This is a constant volume process, and this dA is again a constant volume process. So I can say that for a Stirling engine, AB is isothermal expansion, same as that of a Carnot cycle, and BC is not an adiabatic, but it's a constant volume process, and CD is isothermal compression, while DA is again a constant volume process. This is the theory of a Stirling engine and how it is different from a Carnot engine. And if you are interested in calculating the work done, the net work done would be this one. and it is known that the efficiency of this Stirling engine is less than the efficiency of the Carnot engine. So efficiency of Stirling engine is less than the efficiency of Carnot engine. Practically, the concept of this Stirling engine has been used in automobiles and space aircrafts and in some military submarines. So you can easily compare these two famous types of engine, Carnot engine and Stirling engine, and what are the differences between them. This summarizes our lecture. Now I would look into a numerical to clarify these points for you people. This is numerical number 26 of the book Halliday, Resnick and Walker. A Carnot engine absorbs 52 kilojoule as heat and exhausts 36 kilojoule as heat in each cycle. Calculate the engine's efficiency and the work done per cycle in kilojoule. First, since it absorbs 52 kilojoule, the QH should be equals to 52 kilojoule, and it exhausts 36 kilojoules as heat, so QL should be equals to 36 kilojoule. Now in first part I have to calculate the efficiency. Efficiency is 1 minus QL over QH. It would be 1 minus 36 over 52. This efficiency comes out to be 36 over 52 is nearly 0.69, and 1 minus 0.69 is 0.31, or multiplying it with 100. This engine is nearly 31% efficient. And in second part I have to calculate the work done, and work done is given by QH minus QL. So work done would be 52 minus 36 is equals to 16 kilojoule. So this engine is doing 16 kilojoule of work in each cycle. Hopefully you have understood this numerical and this whole lecture, which was related with second law of thermodynamics. And second law of thermodynamics is that entropy of a system is equal to greater than or equal to 0, and greater than is for an irreversible process and equal to is for an reversible process. However, in all the practical engines the entropy always increases. Then we try to calculate the entropy in real world. First we took ideal, what are ideal cases, then we take a Carnot engine, and afterward we took a Stirling engine and looked into them for different features like entropy, etc., and efficiency. Then we have done a numerical related to these topics. Hopefully you have understood this lecture. I would be back soon with a new lecture. Thank you all.